So I'm looking at a similar sort of task as Mark was looking at, as in sound design, which is an integral part of making and performing electronic music. It involves setting large numbers of timbre parameters. So again, you'll be given a synth like this, and there'll be 40 controls, and somehow you have to set all these controls to get the sound that you want, the texture, the timbre. And this research is looking at musicians in the process of searching for a sound using a synth. So my main question is, which is better, which is faster, serial or parallel control? So given a synthesizer on the left there, you're controlling one thing at a time, and in theory you could be using something like a leap motion hand tracking device to control many degrees of freedom at once. So that synth has about 40 controls, and your hands have about 40 degrees of freedom. So it might be possible to do it much faster. Obviously there's cognitive limitations here, and that's one of the things I'm looking at. Second thing I want to talk about is how you measure throughput for something like this. So I've defined throughput as the rate of information transfer from the user to the instrument. And I want to tell you how to take a search path through a high-dimensional timbre space or parameter space and turn it into an actual measurement of bits per second. And the reason I want to do this is because I have this idea that the expressiveness of an instrument is to do with the bandwidth. So I'm a performer, I'm playing my synth, I want to transfer an idea from my head to your heads in the audience, and I'm using this band-limited communication channel, and the bandwidth of that channel determines how well I can convey an idea and how fast I can convey that idea. So it'd be nice to have a little speedometer on that channel from my brain to your brains. So in science it's good to reduce it to the simplest possible case. 2 sliders versus an XY pad, which one's faster? So we did that, and also looked at 3 sliders versus a 3D hand tracker, so just finding a sound in a 3D box. So the task I can show you, basically the idea is that you're given 2 sounds. One's the target sound and one's your sound, and you're controlling your sound. So you hit current to hear your sound, you hit target button to hear the target sound, and when you think you've matched the 2, you press submit and you get a score back. So it's kind of a gamified sound design task. And similarly for the XY pad, I match them up, I get the bullseye, and I see where I should have been. And there was a couple of different experimental conditions. The next condition is you get the visual target, and you just match the visual target and you press submit. Much easier. So this was to see how good the interface was independently of this sound design. And the final condition was you have to memorize the target sound. So as soon as you hit memorize, the button disappears. You've got to keep that sound in your head and then match it up somehow, which should be harder in theory. So the participants were expert musicians, so they'd had synthesizer experience. They did about 800 trials each, and practice did have a large effect, so we needed to keep them going for about 4 hours over 2 days. And the data we recorded, everything that they did, all the input was recorded as MIDI controller data. So here are some results. This is the 2D task. So on the y-axis we've got the Euclidean distance from the target sound to their sound when they press submit, and on the x-axis the time it took them to find the sound. So you can see that actually people are pretty bad at this, even though it's just 2 dimensions and they're experts. There's a massive range of results, but the basic result was significant though. The XY pad was 9% faster and no accuracy loss. So that's encouraging. If we take it up to 3 dimensions, then the difference was bigger. So leap was 17% faster. So you can see that the pink dots, which are the leap motion, the really fast results are on the left. You can see there's more fast results from the leap motion. So we've already got a conclusion, which is multidimensional controllers are marginally faster, but it's not like earth-shattering. But the more dimensions you have, the faster they get. So in theory, it's looking okay. But it would be nice to have a single measure of effectiveness, i.e. this throughput measure. And it would be nice to use all the data from the search trajectories to measure this throughput. And it would also be nice to analyze these trajectories and find out what exactly is different. So to measure throughput, people have been using Fitts law for 30 years or so. And this is a relationship between movement time and accuracy of hitting the target. So you use that formula, you plot a line, and then you can get the gradient from the line, and that measures the amount of the bits per second that you've managed to input into your task. And sound design is kind of like pointing. So it's a bit like Fitts law task, in that you have a target and you're trying to find it, and there is this trade-off between speed and accuracy. But the problem is that we might have hundreds of parameters on our synth, and we also can't specify a target width. So we can tell them, here's your target, but we can't specify the accuracy in advance. So there's also a couple of other problems with Fitts law. There's a number of different formulae, and it's still debated which one's the right one. And it also seems to require new experiments and new formulae every time you add a dimension, which just makes it a lot of work. So my argument is that prediction is not the same as evaluation. So Fitts law is a predictive law. So if you know something about the task, then you can predict how long it's going to take. But we don't necessarily need to predict how long it's going to take. We just need to measure the difference between our two interfaces. So we just need a generalizable way to measure progress in bits. And progress is entropy reduction. That's what a bit is. It's a measure of information, which is a measure of entropy. And, well, that's what Shannon said. And a successful search trajectory will narrow the space of possibilities. Now, if I show you the actual data, maybe this will become clearer. So this is the actual 2D space that people are searching. And these are all the search paths that people did. And you can see that the target's in the middle, and they're kind of swarming around the target and gradually narrowing this distribution. So if you consider this as a probability distribution, you start off with a wide distribution, and it narrows and narrows and it narrows. And you can actually measure the entropy of that probability distribution using this handy formula here. So we can, at each point in time, we can measure the entropy, and therefore we can measure the amount of search space reduction. And this is a way to do it for a single search path. All you need to know is the Euclidean distance from where you are to where the target is, and then you work out what the volume is, how much you've reduced the volume, and then you can use this formula to work out the entropy reduction. So that's what I did. What we don't want is another version of Fitts law, because there's too many already. But the nice thing is that if you do this formula in one dimension, you get Fitts law back. So the advantages of this approach are that you're measuring throughput at the actual point of interest. So you're measuring how much information has gone into the data itself, how much you've reduced the search space. And it also gives you a simple prediction of how to scale throughput with dimensionality. You just multiply it by the number of dimensions, and that's how the difficulty scales. You don't have to specify a target width, and you don't have to fit any lines or debate over which formula to use. So here are some results of that entropy reduction, and you can see that the leap motion gives a straight line. So this entropy measure is along the x-axis, and the time taken is on the y-axis. So as the line goes up towards the top, the distribution narrows and narrows. So the amount of accuracy is that way, and the amount of time is that way. So you see the leap takes about 3.5 seconds to reach 10 bits of accuracy. So something different is happening with the sliders. It starts off steep, and then it gets less steep and less steep. And that is because the interaction is less efficient. If you're starting in one dimension and your target is here and you have to move in this dimension, it's less efficient. And then you change to that dimension, it's more efficient, change to that dimension, it's much more efficient. So perhaps you can see that the more dimensions you have, the less efficient this starting maneuver is going to be. And you're pretty much not going to be going in the right direction with a single dimension controller. So this is the result with the sound. That previous one was with the visible target. So that's the control test where people are just moving as fast as possible to a visible point. And this is the result with the sound. So this is day one. This is before people had practice. And the leap motion's in pink again, and the 3 sliders are in green. And you can see that the leap motion starts off being faster, but then it takes more time to reach a certain amount of accuracy, about 4 bits. After they'd had a bit of practice, everything got better, but the leap motion got much betterer. And the gradients gone down to match the sliders, and the reaction time was much faster. So the reaction time could be thought of as being the intercept on the y-axis. That's how long it took people to begin to start making progress. And also you can see that the XY pad, which is the red line, has a lower gradient than the 2 sliders. So that means the XY pad was faster as well. So this was the test where people had to memorize the target. They could only listen to it once, then they had to match what was in their heads. And you do lose accuracy, that's kind of obvious. You can't remember it very accurately. So the ones on the right don't reach as much accuracy as the ones on the left. But have a look at the gradients. The gradients are much shallower. So if people were memorized the sound and they tried to do it, they were much more effective at traveling through the space than if they were constantly relying on comparing the 2 sounds. So this is kind of interesting. Like, there's something about people's default strategy is to rely on just listening to the sound over and over again when they could be doing this much more quickly. So this has got to do with this kind of perception action loop where your brain is trying to control the body, controlling the interface, and then the parameters are getting rendered as audio, and you're listening and comparing your goal with what you've actually got. And if we take away that feedback, people are actually more effective at doing this task. And this is kind of interesting. So the moral of this story is that you need, if you want to achieve high throughput with an interface, you need to train yourself not to need feedback. So you basically need to practice. You need to work on your predictive machinery so that you know what's going to happen when you do a certain action. You don't need to listen to it. So yeah, it means work basically. The other thing about the memorization test is that people moved more diagonally through the space. So if they were trying to match something in their head, then they'd change multiple things at once with the leap and the XY pad. Whereas if they were constantly comparing the 2 things, that would kind of force them into a one-dimensional way of thinking, and they would be operating one thing at a time. Which is also quite interesting, because again it's this feedback that's inhibiting the faster cognitive strategy. So the next test I've just done recently is a 6-dimensional thing where you have to match the position and the rotation and compare with 6 sliders. And this is time constrained, so you have to do this really fast. And spoiler alert, there's absolutely no contest. The multi-dimensional control is way, way faster. So at 500 milliseconds, you can achieve nearly 2 bits with sliders, and you can achieve nearly 8 bits with the leap motion. So it's, it's a big difference. So there's 3 take-home messages here. Entropy reduction is a handy, flexible, generalizable way to measure throughput. Musical interface bottlenecks are often due to these slow feedback loops. So it's nothing to do with the interface, it's to do with how much you know and how much you've been training yourself to know the space. And multidimensional controllers are potentially much faster, but only if you do practice in this kind of way. And that's it. Thanks, and enjoy the rest of the conference.
Okay, are there questions for our speaker?
Hi. Can I?
FHITE, Aalto University, Finland. So I'm wondering, you are talking about high-dimensional decrease of freedom and high-dimensional spectrum.